Okay, recording starts. Let me bring back to the PowerPoint I showed you the first time. You know, I like to slow down a little bit here. I just want to make sure everybody, you know, good with the concept. Okay, and you remember this one we showed the first time. Can you see it, by the way? Okay.
Yes.
Okay. You see, now we spent a class or two on the fluid mechanics introduction. Now we got come back to this picture. You know, fluid mechanics, really, we are studying the space, what happens in the space. It's not really, you know, the airplane. Airplane is just a flow disturber, okay? And when it passes through the space, and it creates some movement of the air, right? Okay, hold on, let me turn on the waiting room. A couple of people waiting there. I really, hey guys, I really like you guys to be on time. Okay, start from the beginning. Many of some of the announcement I will give in the beginning of the class. I don't want to repeat every time a new one coming in the classroom. Okay, please be on time. Okay, let's start. You know, 9:30 every time. Okay, okay. So come back to this picture. That's the space you're looking at. Okay, the movement of the medium in that space. That's what the topic of this class. Okay, so in that sense, if you want to describe the movement in that space, well, it's kind of difficult. That's why they put red smoke here, right? Do you see that? Okay, the smoke basically so tiny, the particle is so tiny, basically has no weight. So it follows the movement of the medium, which is the air, right? So then you can see it, okay? Then this is the flow field, okay? Similar idea, if you want to describe it mathematically, okay, which is the first step towards engineering fluid mechanics, right? You have to describe it, right? Mathematically. So you use velocity, right, to describe it. Velocity has magnitude and the direction. So if you can use a vector field to describe the flow, then you will see like arrows, okay, go around it. I think that the one picture later talk about, yeah, look at this. Did you see this one? Right, you have arrows. Let me see, how do I do slide show here? Why it's not slide? Why it's not full screen? Okay, here it is. Do you see the right picture here? So again, we're not interested in, actually we study aerodynamics of the airplane or something, but really we're not interested in the airplane that much. We're interested in the space behind the airplane maybe. Okay, so that's a aerodynamic structure here. It's two vortices behind the airplane. That's what we're interested. So we use, you know, that's the space we're interested in. So we put a lot of vectors in that space to describe the flows. Okay, so in that sense, if you want to study the flow in that space, you probably need a lot of vectors. Okay, one vector is not enough. Okay, so in solid mechanics, one vector is enough. If you have a ball, if it moves, just one vector on the ball, always shows you the magnitude and the direction of that ball. That's it. That's all you needed. Is that right? In solid mechanics, is that what we do, right? Okay. In dynamics, right? You have a vector for the object. Okay, but in fluid mechanics, you're interested in the space. Then you have to have thousands of vectors on different locations to describe the flow. Okay, does that make sense? And when we talk about uniform flow, non-uniform flow, it's really about all those vectors you put it on the screen. Okay, those vectors are exactly the same. Okay, then it's not confusing to me. Okay, of course, it's easy to tell. The vectors in this example, obviously it's non-uniform. None of the vectors are, none of the two vectors are identical. Okay. Is that right? Okay. I hope you fully understand. Then steady state, unsteady. What? Steady state, unsteady actually means you compare two different instances. You take picture. This is a picture on that instance. 1 second later, you can take another picture for the same place. Are these two pictures identical? Okay. That's a question you ask yourself to decide if it's steady state or unsteady. This picture, it's only for one instance. Okay, have thousands of points vectors on it, hundreds of vectors on it. Okay, so if I 1 minute later I take a picture in the same location, same place, it come out, they have different vector fields. Then it means the velocity changes. Okay, it is unsteady. Okay, is that clear to everybody? I just wanna, hey, you know, we have 16 of you here. Okay, last time we have about 30, 25 or something. Okay. I want everybody, when you sit in the classroom like this, and fully understand what I'm talking about. Okay, it's good for you, and save your time to learn. Any questions, any unclear? I want it crystal clear to everybody. Flow field. Okay, think about, always remember this image here, vector field. You choose an area, a space of interest. Okay, have so many vectors on this. Then you describe the flow. Okay, it's the field. It's a word called field, right? It's not a vector of the object. It's a vector field. Okay, it means it's a distribution in the space. Okay, is that good, everybody? Okay, I don't mind spending a long time, slow down everything. It doesn't matter. I like just to make sure I convey the idea 100% to everybody. Okay. This is actually what we talked about it before, because the uniform, non-uniform, steady state, unsteady things, we're gonna deal with it later. Okay, please make sure you fully understand. Okay, how to exit the slideshow. Okay, good. Close the window. Okay, now today we're going to start chapter 2, fluid properties. Okay. We might have, we will have homework problems after chapter 2. I probably will assign some after today's class. Okay, it's not in a hurry, and we probably will have our first quiz sometimes, maybe next Thursday or maybe the following Tuesday. Okay, it's not in a hurry. Okay, let me switch my screen to my whiteboard. Okay. What is this? Okay, this is the last times. I have a notes here. I think it's total 10 pages, now only 5 pages so far. So after I complete this 10-page notes, then I will post this on Moodle. So you will have the notes probably. You still can write notes yourself, make it maybe more detail what you understand. But if you don't, then this is the one I will post. Okay. So that's why you haven't seen it yet on Moodle, because I haven't finished this notes yet. Okay. So I think I already posted the class video on Moodle, right? Okay, so feel free to watch it. Okay, properties. Chapter 2, fluid properties. First of all, the unit system. Okay, I prefer SI unit. Okay. But the English unit we will do English unit 2, both. Okay, so as a 21st century engineer, well, to be 21st century engineer, not yet, right? You need to know both unit system. Okay, and because in many countries you use SI unit, here in this country we're still using the English unit, so a lot of communications possible in the future, and you need to know both, and you need to know the unit conversions. Okay, I think have a conversion software handy. I think in Google basically you can convert unit easily. Just type search, type the unit conversion, right? So it will be easy to show. Okay, but with it handy, I think I always have the unit conversion app in my phone, so sometimes I can easily look at it. Okay, and okay, so I guess that's what I mentioned. I think I will have like a 70-30, you know, SI versus English unit problems for you to solve. But this class will have a lot of video project, doing experiments, those kind of things. It's up to you to what kind of unit to use. Okay. Just a review. What is called system? Did you talk about this in thermodynamics? I think you heavily talked about it in thermal, right? In thermal, you always need to pay attention to a system, right? So what does that mean, system? Anybody? Is system a given quantity of what? A given quantity of?
Numbers?
No, it's not number.
Is it a given quantity of fluid?
Yeah, kind of. Yeah, sure. In fluid mechanics, you talk about the fluid, right? Fluid quantity. It's the given quantity of mass. I know what you mean. Okay, given quantity, but we have defined it for the entire, for all the systems. It's not only fluid, right? So a given quantity of mass is considered as a so-called system. So constant. The mass is constant. Okay, mass is a constant, so that's in a system. So that's why the conservation mass always satisfying a system, because you define it, right? Define it as mass doesn't change. It's a given quantity of mass. Okay. Okay. Well, this is the Newton's world, right? In Einstein's world, the system of the mass is not constant. If you speed is fast, then your mass increases, something like that, right? Yeah. We're in the Newton's world. Okay, good. The third concept I want to introduce is extensive property. I don't know if you ever heard about this. Something called extensive property and the intensive properties. You guys are English speaker. What does the word mean? Extensive, intensive, educated guess? Can you, even without review the textbook, do you, by chance, by looking at this two words, what does that mean? Extensive property, intensive.
Do you mean extrinsic and intrinsic?
No, extensive, EXTENSIVE, and intensive property.
Intensive, independent, and extensive depends on the mass.
Yeah. That's right. I think so. Right? Is that the word?
Actually, my fault, Josh. I know you was talking, dog.
Okay. Yeah. I'm just curious that the word extensive, intensive have the meaning of like something depend on the mass. Is that what it sounds?
Yeah, those are properties from chemistry that you learn.
Okay. Yeah. Good. So I guess you guys know. So extensive is something related to mass. And intensive is, like something per mass. Okay. So it's a rate. It's not not related to mass. For example, density. the density of the fluid, it doesn't relate it to the mass. You know, a big cup of fluid water and a small bottle of water, they have the same density. So the mass change, it doesn't matter, right? It doesn't matter for the property itself. It doesn't change. But some property will change with the mass, right? Like weight, right? Weight. What is weight? How do you calculate the weight of an object?
It's mass times the gravity.
Yeah, mg, right? So of course, the bigger the mass is, more the weight is, right? So it rely on related to the mass. So it's that's so-called extensive property. Intensive is, you know, it's the rate per mass. Okay, so by convention, I don't know if that's the convention in fluid mechanics or in also other subjects. We use lowercase letter, Greek or Latin or whatever letter, lowercase, to represent intensive property. We use capital letters to represent extensive properties. Just like the total, the weight is W, is capital W, right? And the mass itself is, you know, capital M, right? And the intensive property like density, rho, those kind of things, you know, you use lowercase letter, okay? So this class we're not gonna deal with pressure a lot. So is pressure a intensive property or extensive property? Anybody? Pressure.
Intensive.
Pressure is, you say intensive, why is that?
It doesn't rely on mass.
Okay, so let me give you an example. Okay, I have a big tank here. I have a small tank here. Pressure on the bottom of the tank. Does it relate to the mass?
Yeah.
Oh, so it's the extensive property. Who said yeah? Is that right?
I did.
Okay, so do you think it's an extensive property?
Yeah, because depending upon the mass that's on top of it is going to increase or decrease the pressure.
Okay, that's you're right on. If we talk about the force on the bottom of the cup, then it's correct. Okay, it's correct. So yeah, force. The force related to the that's why force is the extensive property. F is the capital letter.
Okay.
Force is extensive property, right? So it's related to the mass mg. Okay, but be careful. That's a common mistake a lot of students made. We're talking about pressure. What's the definition of the pressure? Pressure is, yeah, pressure is not force. Pressure is force per area. Okay. You know, if you're good on those mass vectors, you know, F is a vector, A is a vector, vector divided by vector become a, you know, scalar. Okay, pressure is a actually intensive property. It doesn't matter. P equal to what? In high school physics, you had, no, you probably had in the college physics, whatever physics. P is rho G H. So P is rho G H. If the H for these two cases are the same, how about pressure? Yeah, rho is same fluid, G is a constant, right? So it seems like the pressure on the bottom is the same. Okay, it's not we're not talking about force, it's pressure. Okay, be careful. So in that sense, pressure is intensive property. You have obviously bigger mass in the left tank than the right tank, but the pressure are the same. Pressures are the same at the bottom of the two tanks. Okay, is that clear? Does that make sense?
Yes, sir.
Okay, yeah. I want everybody and understand this. Pressure only changes with elevation. Okay, it is an intensive property. It only changes with elevation. Be careful. Okay, very common mistakes. Okay. Hey guys, come to the class, learn something very useful. Okay. Okay, now let's introduce, oh, by the way, any questions, please jump in, okay?
Can you please repeat what you wrote in the two examples? Where P equals, you
P
said
equal,
rho?
is that rho GH? P equal to rho GH, right? Is that right? Is that what we learned, how pressure, calculated the pressure under, yeah.
Thank
Okay, you are, okay. So, okay, let's introduce couple fluid related properties, okay. Of course, first one is density, rho, it's intensive, right? Lowercase letter here. Unit in kilogram per cubic meter. What is the unit in the English unit, anybody? For density? I don't think it's a pound mass per cubic feet.
Isn't it a PSI?
No,
No, that's pressure. That's pressure. My bad.
PSI is pressure, right? I'm talking about density. What is density? It's the mass per, oh no, I'm sorry. The mass per, yeah, mass per volume, right? That's density. Is that right? So
mass per unit volume, kilograms over meters cubed.
yeah, that's right. That's what I wrote. But my question is, what is the unit of density in the English unit, English system?
The pound force per foot squared.
I don't think so. It's not pound force. You know, it has to be mass. Okay, pound force is the force, right? But it's not pound mass. I think it's not pound mass per cubic feet. It is actually something called slug per cubic feet, right? Okay, be careful. Okay, when you do the calculation, if you use density in the English unit, you have to convert into the slug per cubic feet. Okay. Density, we talk about when we talk about the flow classification, we use the density compressible flow. Did we talk about it? We probably didn't, right? Compressible versus incompressible fluid. We have a name called incompressible fluid and a compressible fluid. Okay, so compressible fluid means the density can change.
We talked
Okay.
about it.
What do you say?
We talked about it.
Oh, we talk about it. Good. Yeah. So then gas dynamic is compressible flow. The density of the gas changes significantly with the change of pressure, with change of temperature, everything changes, the pressure, the density will change. Okay. So for the incompressible fluid, the density not that easily change. Okay, just like water. If you pressurize it, no, it's not gonna change pressure. It's not gonna change density. The volume cannot even be pressurized, you know, it cannot even be reduced even with a tremendous amount of pressure. So this type of fluid, like liquid, we call it incompressible fluid. Okay, and the good thing about incompressible fluid, this is basically in our class we talk about this. The density is a constant for the problem. Okay, so it doesn't change. That make our life much easier. Okay, because otherwise you will introduce a new variables in your equation set. Okay, so it's pretty bad. Then you need to have additional equations. For example, you have to have temperature equations, energy equations. Now, since we don't have density as a variable, momentum equation, conservation mass is sufficient. Okay, so we don't need to bother to look at energy equation. Of course, we're still gonna talk about energy equation, right? But theoretically speaking, it's a closure. We will have enough equations for variables if density is a constant. Okay. Related to density, let me introduce a couple things, couple properties called specific weight. Okay, I think this is new to you. Okay, we probably never taught this in other classes. Okay, specific weight letter as gamma. Okay, it has a similar purpose as density, and the gamma means weight per volume. Okay, now you see the similarity. Density is mass per volume, right? Here is weight per volume. Okay, so the conversion is from kg to mass to the weight. So basically, gamma actually equals to density times what? Kilogram to the weight, the mass to the weight. What's the difference? If you want to convert rho into gamma, rho times what will be equal to gamma?
Gravity.
9.8
Yes,
meters per
yes,
second
yes,
squared.
gravity, gravitational acceleration, right? So rho g, okay. It's a invention, you know, try to make our life a little bit easier on writing, okay? In fluid topics, sometimes equation is long, okay? In fluid mechanics, equations are very long. Equations are very long. So any simplification on writing, you know, it will be good. It will be welcomed. So usually rho and g are always together in the equation most of the time. Okay, so why not we use one letter to replace two letters? Okay, make it a little bit shorter. Gamma means rho g. Okay, just remember, gamma means rho g. It's easy to remember, right? Okay, well, I don't want you to spend any other time after the class try to figure out, oh, what is gamma? What is the specific weight? Okay, rho g. Okay, but the meaning is the weight per volume, okay, instead of mass per volume. Okay, especially in the English system, weight per volume is a good idea because in English system, the weight is a direct, you know, property, right? How to say this? There's a base unit, right? In the SI system, what are the base unit? Time, right? Length, second, meter, okay, and the mass, okay, and what's the other one? Just the three base units, right? English system. Also, the second is the time, length is feet, right? That's the base unit. But the mass is not a base unit in English system. It's a force, pound force. That's your base unit. And your mass is a derived unit from pound force. Am I right? Am I right on this? So in that sense, weight per volume is pretty straightforward in the English system. It's just a pound per cubic feet. Both are the base using the base unit. In the SI system, density is more natural because mass is a base unit. Mass per cubic meter per volume. Both of them are base units.
Dr. Zhang,
Yeah.
so if weight per volume is just pound force per meter cubed, then what is a slug in relation to pound? Like, what is a slug represent?
I forgot. It's just a relation between pound mass and the slug. They're the conversion. Okay. Yeah. And the pound mass is you can directly get it from pound force. I think. Then yeah, and then the conversion to the slug. And so what I try to say is gamma specific weight in the English system is very natural because both weight and the volume, cubic feet, are the base units. Okay, in the SI system, density is more natural because both mass and the cubic meter are the base units. Okay, so that's why they invent this specific weight. So it's comparable to the density. Okay, but the good thing also about gamma is shorter. It's rho g. Rho times g become gamma. Okay, so in the equation, maybe you use one letter instead of two letters. Okay, that's also one advantage. Okay, this is specific weight. And there's another specific. It's called specific gravity. Don't confuse two things. These are totally different things. Specific gravity. It's heavily used in industry. Okay, both rho and the gamma are the dimensional variable, so property. So it has units. Okay, so just like say unit conversion, different country, different system, you have to different unit you have to convert. It's kind of complicated sometimes. You remember in 2001, 20 years ago, there's a Mars mission, the first Mars rover they sent it on Mars. Fly like almost more than a year, then reach Mars, then they deploy it, then it's a failure. The first one, the failure, I don't know if you remember. You're probably not old enough to remember that the first Mars rover actually is a failure. Okay, it didn't success. Okay, then they spend billions of dollars on that. Then eventually they find out that's because the one engineer, it's SI system. He confused with the English system. So the unit conversion part is wrong. So the calculation actually the result is wrong. That's why leading to a very expensive failure. Okay, so that's exactly what happened. So be careful. And then the unit are complicated. So what if we can invent something, some variable, some property that without unit, the so-called dimensionless property? Then it's easier. It's easier to communicate between different countries, different engineers, right? So we use specific gravity. It's called S. Okay, specific gravity is the density of your fluid divided by the density of water. Oh, by looking at this expression, it's easier to understand. It's a ratio. Okay, the ratio to show how heavy your fluid is. Okay, comparing to what? Comparing to a reference, which is water, commonly used reference. Okay, so it's a ratio. So you have, if you have for your fluid, unknown fluid, let's say you have a specific gravity of 0.85. Can you find the fluid, the density of that fluid? See, what does that mean, 0.85? What does it tell you first when you just see the number 0.85? The specific gravity of that fluid is 0.85. Does that mean
85% of water?
does that mean its density is lighter than water?
Yes.
Yeah, right. See, 1 is the number. It's a border. If it's greater than 1, that means hey, your fluid is heavier than water. Okay. If you're less than 1, lighter than water. How much lighter? You're right, 85% of the density of water. Okay. If density of water in SI system is easy to remember, is 1,000. Okay, that's the advantage of SI system, right? Those numbers are easy to remember. So the density of water is 1,000 kilogram per cubic meter. So what is the density of your fluid if the specific weight gravity is 0.85?
It's 850
That's right.
cubic meters.
Yeah, it's very easy, right? It's easy. You don't even need a paper. Okay, pen, paper. You don't even need that. Okay, if you talk about specific gravity 0.85, okay, that's 850 kilogram per cubic meter. Okay, is that kind of like a oil, crude oil, 0.85? I don't know. I'm just making up numbers. Maybe crude oil is a little bit heavier than 0.85, right? Maybe 0.9-ish. Okay, also depend on the oil from Saudi or oil from Venezuela, right? So the really from Saudi is lighter, right? So, okay. So this specific gravity is actually heavily used, okay? Is actually heavily used because the industry, indeed, they have sometimes have problem with units. So why not we just use a specific gravity to talk about what is the density of that fluid, okay? So if it's 1.3, so it's 1.3, it's heavier. Okay, we can easily figure out the density based on that number, okay? What is the heaviest fluid? I don't know, it's absolute heaviest or not. Probably mercury is one of the heaviest fluid, right, in the world. So what is the specific gravity of mercury? Educated guess. Mercury, anybody? 10-ish or 100-ish?
What's the specific gravity?
Yeah.
Uh,
Well,
Two.
it's educated guess, you know, it's 2 or 5 or 10 or 100 or 1,000. Educated guess, approximately. Sometimes engineer needed some approximation skill, right?
12.
12 is pretty close. It's
13.6.
That's right. 13.6 in mercury, so pretty heavy. Okay, more than 10 times of water. Okay, and now we have a new specific weight, right? Can you use the specific weight to make this expression instead of using density? Gamma fluid, your target fluid of gamma water. Same thing, right? Because gamma just same as density, just have a g there. G is a constant. If you talk about ratio, the constant g can be canceled, so they are equal. Okay, density ratio and gamma ratio are equal. Okay, they both are represent a specific gravity. Okay, is that clear? So these two we're gonna heavily used in this class, gamma and the S, okay, specific gravity and the specific weight, instead of using density. Okay, that makes sense, everybody? Please fully understand. Just remember it now. I don't want you to spend time after class just trying to find out what is specific weight, what is specific gravity. Can you? How many we're here? Not many, 16 of you. Okay, at least you're benefiting from attending the class, I hope. Okay. Any questions? Is that good?
yes, sir.
Okay, good. Let's continue. The next one, the next property is very, very important. Okay, it's a new property. Never talked about it in solid mechanics. Only have it in fluid mechanics, about viscosity. Okay, so you know the fluid is viscous, right? Well, you can have examples like what, like a bee honey. Is bee honey a fluid?
Yes.
Yeah, obviously it's a fluid, right? It flows. So is it sticky? Okay, so sticky basically means actually it stops the flow from stops the fluid from flow freely. Okay, that's the property. Like how sticky the fluid is means if you have the fluid is sticky, then it flows slowly. Okay, it can freely flow. Okay, some of the like to me like a resistance in the fluid, you know, to stop it from moving fast. Okay, so less viscosity means the flow can more freely move. Okay, so I used to have a example one time. I just did it one time in class. It's too messy, and I stopped doing it. You know, I have a slope, you know, a slope like this, and I have a cup of water and a cup of bee honey. Let it flow down the slope. Okay, obviously the water flow much faster than the bee honey. Okay, so it showed the viscosity. One had high viscosity, one had the low viscosity. Okay, so but I want to give you a example to show actually how the viscosity works, you know, microscopically. Okay, I give you a very, very simple examples. You know, I'm gonna use this example throughout the semester in many different applications, but this is a typical example, classic example of a flow over a surface. Okay, so I think I use this example a lot because I want you to know, although you cannot see the flow, okay, I want you to know what happens of the fluid near the surface. Okay, this is the space we're interested. Again, we're interested in the space above above that surface, right? This is fluid mechanics, always interested in the space, okay? So the space above the surface, okay? Let's use a velocity profile, okay? Let's say, hey, I choose a location, a line, okay? I want to see how does the velocity changes along that vertical direction, okay? Along that profile line, okay? See, at the far away from the surface, of course, just the regular flow, just the free stream velocity, right? Is that right? Everybody follow me? If it's really far away from the plate, then you don't feel the plate. If you are the fluid, you really don't feel it. You really don't feel the existence of that plate. So you just flow with the same velocity as the incoming velocity. Is that right, everybody? Okay. On the other hand, on the wall, exactly on the wall, the velocity is fully stopped. 100% stopped, is 0. Okay, they call it non-slip boundary condition. Okay, that's because the viscosity, the property of the fluid, serves as a resistance to the motion. Okay, when you reach to a surface, okay, when you reach the surface, it's pretty obvious. Okay, so what happened to the velocity profile? So okay, on the wall is 0. Okay, when it's far away from the wall is just the free stream velocity. Okay, doesn't change. So how does it change velocity profile? Is a straight line linearly change? It's not really linearly change. It changes like this. So if you draw vectors on every location along this vertical line, you will see how the velocity actually changes. Okay, I need to ask you, do you understand my drawing here? I use vector. I assume you know what the vector means. Need any explanation on this? Everybody, is that clear? Is that good?
I do have a question.
Okay.
Is that supposed to be representing a solid wall, or is it just a?
Yeah, this is a
just like
solid wall. It's a solid wall. It's a physical wall. Okay, that's why it can stop the flow, because you have the viscosity of the fluid.
Okay.
Okay. Just like water, you cannot see clearly. If you see the bee honey flowing down, actually is obviously, if you look very, very close to the fluid, you see the top far away from the wall, actually it flows. Okay, when the honey close exactly on the wall, it's not flows. So gradually, basically, it's on top of the bee honey is flow down, flow forward, then reach the ground. Gradually, always the top layer flows, right? So that shows the viscosity effect. Okay, then so if you want to zoom in this area, okay, if you let's draw a, let's say, hey, we're looking at the finite, infinitely small fluid element. Okay, let's say before you enter the surface, the fluid element is like this. It's the listen, it's the infinitely small fluid element. You can only see it by like what, microscope, or enlarge like a billion times. Okay, let's say theoretically, infinitely small element. Let's say it's look like a rectangle. Okay, adjacent to the wall. So you have a bunch of those elements stacked up for the fluid. If they move at the same rate, same speed, so there's a stack of elements move forward, right? Okay, so what happened for this element when it reach to the surface? In here, then this element actually changed the shape like this. Okay, the bottom of the element is exactly stick on the wall. Okay, is that right? And top, because it's a little bit away from the surface, then it pushed by the flow, it pushed away. So it forms a deformation of the fluid element. It forms a deformation of the fluid element. Okay, the deformation is due to the viscosity. Okay, think about it. If there's no viscosity of this fluid, then even on the ground, it won't stick to the ground, and it will just go. It's just still freely go, keep the same shape all the time. Okay, it just slide it over. Okay, but now since it has a viscosity, the bottom of the element stick on the ground. At the end, it's not moving, but the top of the element is still pushing it away. So it caused some deformation. Okay, that's what really happened in the fluid. Okay, near the surface. Okay, so this is called deformation. Okay, so I think in previous class you talk about the deformation and something called strain rate, right? Strain rate representing the deformation. Okay, so the force try to move this element is the force like a shear force, right? Let's say shear stress per area. Is that the shear? Do you know what I'm talking about? The shear force, like a scissors. Like to this element, it's like a shear, right? You have a force on the surface to push it, but the bottom is going to something holding it. So it's a shear force. So people knows shear force is really related to the strain rate, which is du over dy. Okay, du over dy is what? The change of velocity. Basically, you can look at it. If you looking to put into a triangle, this is du. Okay, this is delta y. Okay, du dy representing the tangent of this angle of the deformation. Okay, so so-called strain rate. Have you talked about this in strength material or other classes? I
Yes,
hope.
sir. Yes, sir.
Yeah, great. So people knows the shear stress is proportion to the strain rate. So that's a definition of the fluid, right? Did I say it last time? The definition of the fluid from the textbook is what? It's continue to deform under the action of a shear stress. Bingo, it's exactly this equation. Under the action of a shear stress, okay? See, they have a shear stress or pushing the flow, right? Moving the fluid. Then under the action of this shear stress, this fluid element deformed. Okay, deformed. If you look closely, yeah, it's deformed. Okay, this is definitely is just follow the definition of a fluid, right? So, and du dy is what we use to describe this deformation, the strain rate. Okay, and the cause and effect. So shear stress is the cause of the deformation, and the effect is the deformation. Okay, so this is kind of dynamics, right? Dynamics we will study force and effect. Okay, so but we need to have the equation. This is not equal. Shear is tau is not equal to du dy, obviously. You look at the unit, they're even not the same. The shear is like a force per area. Du dy is what? Meter, meter per second divided by meter is like 1/2. So the unit is not even same. How can you equal them? You cannot, right? The engineers are smart, they're not equal, then we force it to equal by adding a coefficient. You always can multiply by a coefficient and make them equal. There's some coefficient there, right? Okay, if they have relations, cause and effect, if they have this kind of relation, you always can equal them by adding a coefficient. And what is a coefficient? You can experimentally determine. That's actually a real process. In the future, a lot of you dealing with some engineering work, you have to create a coefficient and make something equal. Then you can explicitly, independently measure that coefficient, and then you solve a problem. Okay, so that's what we do. We made the equation equal. Okay, I know then there must be some coefficient there, and to make it equal. I know the shear stress is related to the strain rate, but I don't know how much their relation is. So I put in that coefficient. That coefficient is called dynamic viscosity. Okay, so viscosity is a property. Okay, dynamic viscosity. I think the unit is what is Newton second per meter square. Okay, so you can derive this unit from the equation itself, right? This is Newton per meter. This is 1/2. So 1/2 moved to the left hand side is Newtons times second per meter square. That's the dynamic viscosity, the unit of it. Okay, so if you want to use a kilogram base unit, you can Newton equals to MA, right? So force equal to MA, so it's kilogram times meter per second square. So if you want to replace Newton by the kilogram meter per second square, then it becomes a base unit. Okay, it's up to you how to which one to use, but this is the unit for the dynamic viscosity. Okay, so mathematically we describe the fluid by using this equation, and the mu is the viscosity, and that's the property, very important property. So the bigger the mu is, more sticky the fluid is. Okay, smaller the mu is, less sticky, right? Okay, more dilute that fluid looks like. Okay, any question on this? Important, this is the new property, really 100% new property, right, to you. Any question? Yeah, understandable. Viscosity is used to describe how sticky the fluid is. Okay.
I have a question.
Yeah, go ahead.
How does viscosity relate to the Reynolds number? If you know that.
Well, Reynolds number is nothing to do with this, right? Reynolds number is this. Yeah, good question. Then we can talk about it. Reynolds number is rho u length divided by viscosity. Okay. So convection inertia versus the movement speed versus the anti-speed, basically. That's Reynolds number. Okay, and that means the larger the Reynolds number is, less viscous the fluid is, faster the fluid is. You know? The lower Reynolds number is, the stickier the fluid is. Yeah, you're right. This is related because Reynolds number basically partially talk about how sticky the fluid is. Okay, good question.
Okay, thank you.
You're welcome. You are like 10 steps ahead already. Good. Okay. Okay. This is called dynamic viscosity. Sometimes people use something called kinematic viscosity. Okay. Dynamic versus kinematic viscosity. Okay. Kinematic viscosity is mu. Okay. It sounds similar. Mu. Okay. Divided by a density. And the unit is easier for kinematic viscosity. That's why people use kinematic viscosity a lot. Is meter square per second. If you divide it by the density, then the viscosity becomes meter per second. Then you get rid of the kilogram in the unit. Sometimes people like it. Okay, it kind of like shows the diffusion effect of the fluid. Okay, meter square per second. How fast the fluid is diffused. Okay, it's kind of, I use big words here, diffusion, diffuse.
Can you read what that says?
Dynamic versus kinematic viscosities.
No, the letters underneath. I don't know what that is. That, did you scratch something out? Is that what that is right there?
I scratch something out. Okay, it's a new. Nu equal to mu divided by rho. Is this Greek letter, nu and mu? Huh? Do you by chance know? Or Latin? Or I'm not good on this. I just was taught the letters, but is that Greek? I think it's Greek, right? Anyway, it's called nu. Look like a V, right? Look like a V.
Yeah, it's great.
It's Greek, right? Yeah. So nu representing the kinematic viscosity. The mu, like a U, right? Mu, that's called. Mu is the dynamic viscosity. Okay, so there's a conversion from dynamic viscosity to kinematic viscosity. It's just divided by density. It depends on, usually in the engineer handbook, you have the property tables, the both of them will be there. Usually nu and mu will be there. Okay, depend on which one you like to use. Okay, but they're the same thing, basically the same thing. It's a density difference. Okay, most of the cases we deal with incompressible fluid, the density is the same, it's a constant. Okay, so, okay. Well, this is the diffusion. People call it the diffusion coefficient, mu. Okay, look at the unit, the meter square per second. What means diffusion? Okay, I like to at least understand the two words, convection and the diffusion. In fluid mechanics, the motion of the fluid is by these two factors, these two effects, convection and the diffusion. Are you in heat transfer class? Many of you are, right? Any of you are in heat transfer?
Yes,
Any
sir.
of you? Yeah. Did you start talking about the conduction, convection?
Yes.
Okay. So see, heat and the fluid are basically the same thing. Okay, they're the movement of you in the medium. So both are driven by heat and the fluid. Both are driven by these two factors, two effects: convection and the diffusion. So what is a convection? So convection means the directly flow, wind blow to it. Okay, for example, you're sitting, you're standing in front of a fan. Okay, fan blow air to you, you're directly hitting by the air. Okay, convection by the flow. The property change by the flow, basically, it's called convection. It's property change due to the flow. But diffusion is more interesting to in the nature, they always has a diffusion effect, not only for fluid or for heat transfer. In heat transfer, what is the diffusion effect? I think it's the conduction. Okay, you have a heat source, for example. Okay, then you stay close to it. Gradually, you will feel the heat go reach you. Then you will feel the heat. Right? That actually in heat transfer, there are two factors in there. It's one is the diffusion, they call conduction, heat conduction. So the heat will reach you without needing any given mechanism. You don't need a force to make the conduction happen. You don't need anything extra to make it happen. It will happen by itself. So nice. Without using any energy, the heat just go from the high temperature to low temperature. Okay, that makes sense. It's called conduction. In a conductive material, for example, you embedded a heat source there. Soon, in the outside of the material, you will feel the heat. You will feel the hot temperature, because hot temperature can just transfer to you in the medium without needing any source, without needing any energy. Okay, so it will transport naturally by itself. But you have to have a requirement. You need to have a temperature gradient, temperature difference. You have to have a high temperature. You have to have a low temperature. Then the temperature will go from high to low, always. Okay. In heat transfer, we call it a conduction effect, but actually is one of the diffusion effects. Okay. As long as you have a high concentration, whatever, and not only temperature, high concentration. Okay, it will naturally go from high concentration, you can go to low concentration, eventually go around it, dispersed. Okay, just like in a fresh cup of water, you drop a grains of salt in there. The salt has a high salinity concentration. salt, the water has low salinity concentration. Immediately, when the salt reaches the water, it will dissolve. Eventually, in the entire water will become same salinity. You lose the high concentration, it will be evenly distributed to the low concentration. Okay, you don't need energy for that. But in thermal, we learn something called entropy, right? Entropy from low to high. You know, in the initial high concentration situation, you have very low entropy. Then eventually evenly distributed into the entire cup, then become high entropy. Okay, entropy always from low to high. Entropy always generating, always possible. That's what God makes the world goes. It's very fancy to me. Okay, so this is called diffusion effect. It's a salt dissolve. Okay, you don't need the extra force. You don't need to add extra energy. It will just go from high concentration to low concentration always. Okay, same thing to the fluid mechanics. If you have a point has a high speed, that high speed will always diffuse to the surrounding. Well, you know, nearby you will feel a little bit getting a little bit faster too. Far away from it, a little bit by little bit, right? So the high concentrated speed also will be diffused to the surrounding. Makes the surrounding has a little bit of speed too. That's called diffusion. Okay, and the viscosity is also called the diffusion coefficient. Okay, it leads to a diffusion. Okay, that's another factor, another effect from the viscosity, viscous of the fluid. Okay, so that's viscosity. That's what I want to talk about, viscosity. Okay, that's the equation. Okay, here, this is the first equation I introduced in this class. Okay, this equation, today I don't have enough time to give you an example. I have about 10 minutes. Okay, next class I will give you a example to use this equation to actually solve a problem. Okay, this is the first equation we introduced in this class. Okay, shear stress of the fluid equals the viscosity times the velocity gradient, vertical velocity gradient. Okay. Oh, by the way, some book you see it's use v as velocity. Here, the reason I use u as velocity is particularly for this problem. Velocity is a vector, right? Vector, you have 3 components. So by convention, we use 3 letters to representing the 3 velocity components. Okay, so u is the x component velocity, v is y component velocity, and w is z component velocity. So at any given vector, you can decompose into velocity components. This is u, this is v, and if you have a third dimension, then it will be w. Okay, so for this example problem, I give the u. It is only one-dimensional flow, right? The flow is just x. This is assumed without saying anything. This is assumed to be x direction, right? So that's why I use u here. Okay, I like to always be specific. Okay, since we're talking about the u x direction velocity, I use the letter u. Okay. Sometimes books just use the letter v representing the velocity. Okay. So I'm not going to give you a actually example to solve, but let me describe you to some of the characteristics of the viscosity. Okay. So viscosity changes with temperature. Okay, viscosity change with temperature. Do you have any examples to showing, obviously to show that velocity change with temperature?
Lava.
But how do you show it change with temperature? So lava is hot, like 600 degrees right now, Celsius, okay? When temperature changes for the same fluid, same lava, temperature become 100 degrees, then what happens? It move faster or move slower?
It moves slower.
It moves slower. That means the viscosity increased or decreased when temperature decrease.
It increased.
Yeah, viscosity increases when temperature decrease, right? That's an example to show.
I mean, it's
Actually
just the movement of the particles.
Yeah.
If something cools off, the particles move slower.
Yeah, we use this viscosity to describe that effect. Okay, it moves slowly. Then when the temperature decreases, so that means the viscosity increases. Oh, by the way, let me ask you a question before I do this. You have the equation here, right? So can you relate this to solid mechanics? What is a viscosity for a solid? Anybody educated guess?
Isn't it just one?
Why is one? Why one is so unique, so special?
Is it friction?
Huh? So I'm just trying to use this to give you a skill that when you look at the equation, how you reflect it to the reality. Okay, I want you to do that. I apply this equation for the solid. So if the solid, okay, if you apply a shear stress to the solid, hey, let's say I have a block. I try to cut it with my hand saw. Martial art. Okay. What happened to the let's say a solid block, let's say a copper. Okay, I have a copper block. I have a gold block. How about that? I just try to use my naked hand, try to cut through it. So apply a shear stress to it. What happened to that gold
If
block?
you're using your hand, nothing's gonna happen.
Nothing gonna happen. Okay, but I do apply a shear stress to this block. Okay, and nothing happens. So can you use one of the term in this equation to tell me nothing happens? I apply a shear force. Okay, shear stress is non-zero. Okay, and nothing happens. That means what? Does it deform?
No.
No, it's not
So it's
deformed.
solid.
So which term is zero?
Mu.
Hmm?
Mu.
No, it's not mu. Which term representing the deformation? Did I say the deformation? Shear stress is related to strain rate. What does strain rate means? Strain rate means deformation. Rate of deformation. So which term here in this? There's three terms here, right? Tau, mu, du dy. Okay, three terms. Which term representing the deformation?
Dy.
Du dy. Okay, so if the golden nugget, the golden block doesn't deform, what the du dy equals?
Zero.
Equal to zero. Okay, now you look at the equation for the golden nugget. Tau, I apply a tau to that golden nugget. Du dy is zero. How can this equation still be equal?
The shear stress would just be zero.
No,
Right.
it's not. Shear stress now. I apply a shear stress to it. I apply a force to it, right? It's not zero. How to make this equation even still stand, still valid? If you have no deformation.
E to the 0.
Du dy is zero, okay? Du dy is zero. 100% sure, right? Everybody clear? Du dy is zero? Okay.
Just get rid of it.
No. Come on, guys. Educated guess. What can you play with? Tau you cannot play. I apply 100 Pascal force, pressure, shear stress on the system. Okay, there's a value there. Du dy is zero. Anything you can manipulate? So what is the viscosity of the golden nuggets? Hmm? a non-zero number equals to something viscosity times 0. Okay, what is the only chance this equation still can be valid?
Well, you have to remove the 0 somehow, so that
No,
way.
don't move. Just tell me what happened to the mu if I want to make this equation still possible to be valid. A finite number equals to viscosity times 0. What happened to viscosity? What the viscosity has to be?
It didn't have to be the same as the shear stress.
No. The same as shear stress times 0 is 0. I said shear stress number is viscosity times 0. This is number is not 0. Okay. Finite number. I say let's say it's a number C. Okay. In this particular example I gave. What's the only possibility for the mu, for the viscosity? So every number you try there, it's not equal, right? Whatever number you times 0 should be equal to 0. Is that right?
Yeah.
Okay. That's only exception.
It had to be an imaginary number or something.
It has to be infinite. Infinitely large. The infinitely large number times 0, it might not be 0 because it's infinitely large. Okay.
Is that how that works?
Yeah, that's how that works. In solid mechanics, in the golden nuggets, what's the viscosity of gold? Do you know?
Infinitely large.
Infinitely large. That's why we don't use viscosity in solid mechanics. But
Okay.
this equation is still valid.
Okay.
All right. I just want to draw this conclusion. Okay. This equation you can apply to solid mechanics too, but that's why we don't use viscosity for the solid, because viscosity of the solid is infinitely large. Think about it. The larger viscosity, that means more harder the fluid is. Harder. Infinitely harder, then it becomes solid.
What? But how does infinity times 0 equal a constant? Isn't it undefined?
It's undefined. It's not, at least not equal to a 0. Okay, ask your math teacher. You know, that's the definition for that. Infinite
I don't think it
0.
could be proven, right?
That's the only chance. Actually, I should say that's the only chance the equation is valid. That's only chance. Okay, not necessarily say it has to be, but that's the only chance when the viscosity become infinite. At least it's not equal to 0. The equation. Okay, you can say undefined, but it's not 0 anymore. It's a little bit better, a little bit closer to the problem. Okay, well, that's what I try to say. That's why people don't use viscosity in solid mechanics, because it's too large. Okay, but strictly speaking, you know, there's no 0 definition. They're always a little bit deformed for the golden nuggets. Even you put in your hand knife on it, it have like a microscopic deformation in there. So your du dy is not really 0. It's a small number, very, very small, but not 0. Okay, so your mu is very, very large, but not infinite. Does that make sense? Then you can equal to a C, equal to any constant, as long as du dy is not absolute 0. Okay, then you will have a huge, huge, huge viscosity to make this equation valid. Does that sound more reasonable?
Yes and no.
Okay, I'm out of time. This is not really serious. Okay, just like for your information. Okay,
Yeah,
so for your information, this is proof that the solid has actually, if you really want to force to use the viscosity for any material, you can, because solid indeed has its viscosity, has its really, really huge 3 trillion, maybe that's a number for a solid matter. Okay, so the equation actually still works because there's always not absolute 0 du dy. You have always slightly deformation, whatever force you apply to it, any material. Still, you can have a slight non-zero deformation du dy. Okay, you have a little bit of movement. Then your viscosity will be huge. Then it will be equal to, for example, 10. 10 Pascal is the force shear stress I'm putting on it. Okay, then it's not infinite and not zero anymore. Right? That sounds better explanation.
Yes, sir.
Okay, that's good. Okay, let's continue next time. I'm really out of time here. Let's continue on the viscosity change with temperature topic. Then I'll give you an example next class. Okay, then let me assign homework problem after next class. How about that?
Okay.
Okay, sounds good. Have a nice weekend.
You too.